Everybody doing? How's everybody doing? There we go. I gotta check this mic though. Okay. So I'm Shua Sanchez. I'm a physics PhD student at the University of Washington. I do solid research. Yeah, okay, there it is. Alright, so basically studying crystals. There we go. Huge bag of this, yeah, okay. That's fine, that's all good. Okay, so I check. Okay, sorry about that. So, I grow magnetic crystals. So I use over 60 kinds of elements that are ground up into little pieces, and I put them into glass tubes, get them over 1,000 degrees hot, cool them down, and then they go from being small pieces into full crystals. The ones I'm going to talk to you about today are arsenic, barium, iron, and cobalt. And if you didn't know, iron and cobalt are two of the most magnetic elements that are commonly found on Earth. Alright, so I have a video that I made, and I'll post a URL at the end of the talk showing how we grow the crystals. But basically, we cool down the glass tube, crack it open, and you can see these little pieces of the crystal. And under the microscope, we use tweezers and razor blades to cut the crystal into different shapes so that we can do experiments on them. And then we glue wires on them. And then once the wire is on them, we put them on a chip. And on this chip, we can measure different kinds of physical properties in the crystal. So, I want to talk about my research, but I want to back up and talk about how your computer uses information, because ultimately I'm growing these crystals and studying their properties so that we can use them in computers and use them for information storage. So there's the computer, right? Alright, so what is information? One way that you can define information is it's a difference between two things. So if you have choices, if you have differences, that gives you information about something. So a yes, no, a hot, cold, an up, down. Your computer likes to store, your computer likes to use just two states. So you have a 1 or a 0. And from 1s and 0s, it can do anything that your computer does. It doesn't need a 2. It just uses more 1s and 0s. So, like a word in a computer is just 8 of these 1s and 0s put together into a byte. So once you have a byte, that's like a single word that your computer uses. So for instance, if your computer wants to store numbers, it will do it like this. It has a code of 8 1s and 0s that tells it it's a 1, or it's a 255, or it's an A, or a Z. If you have a really complicated symbol, you might need a lot of 1s and 0s, but this is exactly how you code it. Just like that. Yep. So your computer sees those 1s and 0s and it spits out that emoji, right? So you can actually encode information in a lot of different ways. Any way that you can make a two-state system, you can actually make a computer or an information storage device. So for instance, in black and white, a barcode. All this is you have a scanner that looks at the black and the white bars and turns them into 1s and 0s. So for instance, Seattle Science Slam in barcode is like that. The URL for this event is in this 2D barcode. All that 2D barcode are just layers of one-dimensional barcodes stacked on top of each other. And you can make these if you just Google, like, make barcode. You can encode information by making things go faster or slower. So for instance, what Wi-Fi does is it has 1s and 0s inside of your router, and it sends out a radio wave. And it makes the radio wave a little bit faster, and that's a 1, and a little bit slower, and a 0. So your computer takes these radio waves and decodes them into 1s and 0s, right? You can encode things with like being full or empty of charge. So every computer is built out of transistors. Transistors can be full of charge or empty of charge. And when you measure charge, how much charge is in the transistor, that gives you a 1 or a 0. And when you put 8 transistors together, then you get a byte. So again, 8 1s and 0s gives you a word. So when you see that a solid state drive has 1 gigabyte of storage space, that's literally 1 billion of these 8 transistors put together, and each one is coding a single letter or number. So you need a whole lot of them for a computer to work, but now we're getting really good at building them out of transistors. There's some problems with transistors though. They take a lot of energy because you have to put into transistors. So there's actually a way to store information that takes very little energy, and you store it in like a difference of up and down. So now finally we get to talk about magnets. Alright. So a magnet, we usually talk about magnets as having a north pole and a south pole. And what that means is that if you measure the magnetic field by the north pole, it comes out of the north pole and it goes into the south pole. But north and south are just names. We can also call them 1 and 0. And what I mean by that is if we measure the magnetic field above the magnet, if it's coming up, we just call that 1. If it's pointing down, we call that a 0. It's that simple. So the way this works is you have atoms with a positive charge in the middle, negative charge electrons around the outside, and all of those electrons have a small amount of magnetism towards them. Most materials are not magnetic because those electrons don't work together to make a strong magnetic field. Most of the electrons just point in random directions. You know what I'm talking about, right? Yeah, you feel me. But if you get all of these magnetic fields from these electrons to line up, you create something called a ferromagnet. So most of the magnets you've encountered in life, they are this class called ferromagnets. Ferro meaning iron, so iron-like magnets. So they work together to make a large magnet. So for instance, in your credit card, you all know that a credit card has a magnetic stripe. Really all it is are just different sequences of small magnets that either point one way or the other way. And then if you only look at the top half of the magnetic strip, then you get your 1s and 0s out of that by measuring the magnetic field coming out of it. The same principle works for a magnetic hard drive. Really all this is just like a whole bunch of credit card stripes, and you just store 1s and 0s in them. And as it spins around, let's see, as it spins around, this tip right here just reads the magnetic field above one given spot, and it says it's a 1 or it's a 0. And that's just how it reads it. So there's a problem. There's actually 2 problems with storing information with ferromagnets. Actually, before I talk about the problems, I should talk about the advantage. Once you store information in a ferromagnet, it will basically stay there more or less forever. So you might have heard that the direction of the magnetic field of the Earth changes over thousands of years. Has anyone heard that before? The way we know that is because every time a volcano goes off, there's liquid iron that comes out of the volcano, and as it cools down, the little magnetic fields and the electrons of the iron align with the magnetic field of the Earth, and then they're frozen in there. So, find lava from millions of years ago, that's still pointing in the direction of the Earth's magnetic field from millions of years ago. So they're excellent for storing information, but they have a weakness. If you stick a really big next to a ferromagnet, it will just realign with the big magnet. So if you have your credit card and you take just a kitchen magnet on it, all of the little magnets that make the magnetic strip, they're just going to realign with the external magnetic field. You lose all of your information from it. The same thing happens to a magnetic hard drive. You take a computer hard drive, you stick a really big magnet on it, like you just lose all of your info. Like it just completely wipes out. Like it's just dead. And this doesn't happen to a solid state drive because it stores information with electricity, not magnetism. There's one other problem really quick with the magnetic fields coming off of these tapes. It's always on. You can't do anything to turn off the magnetism. You can't do anything to stop that. So someone can walk by, and if they have a sensitive enough magnetic field reader, they can like get your credit card info without even touching your card, just by being near it. That's why a lot of cards have switched to using chips. Okay, so now finally we can talk about we can talk about anti-magnets, which is what I actually study. So the one property would be anti-ferro magnets. So in this case, what's going on is you can see that every one of these atoms, the magnetic field from the atom in this direction, they line up in the same direction. But in this direction, they go opposite of each other. So what this does, the magnetic field of every atom is canceled out by all of its neighboring atoms. So this ends up being a perfectly non-magnetic crystal, which means you can't measure a magnetic field off, which means if you apply a really large field to it, like it really, like nothing happens to it because, there we go. Okay. Yeah, so the field coming from the neighboring atoms is many times stronger than the applied field, so it doesn't reorient itself. So a credit card, you need about 100 times the Earth's magnetic field to wipe it out. With an anti-ferromagnet, you need around 10 million times the Earth's magnetic field to wipe it out. There we go. Okay, so then there's this question of how do you actually get information out of an anti-ferromagnet? So if you look again, there's a symmetry difference between the two directions. Along this direction, all of the magnetic fields point with each other, and along this direction, they point opposite each other. And what does happen in the crystal is the magnetic field inside is zero, but there's a lot of other properties that are different because of this magnetism asymmetry. So if you measure the spacing between the atoms in one direction versus the other, it's actually different. If you measure the electrical conductivity of the crystal along one or the other, it's very, very different. If you shine light on the crystal along one direction or the other, you get different frequencies of light that reflect off of it. So the thing about anti-ferromagnets is that people don't really use them yet for devices. For me as a physicist, what I'm doing is studying the basic properties of this new type of materials that aren't really being used for anything yet. But because they're really secure, for all the reasons that I just told you, we think that maybe 20 years from now they could be being used as storage devices. And you could read that information based on the light polarization coming off of the crystal, or the changing conductivity, or the change in the stiffness along the two directions. These are all things that we could use to store information in this type of crystal. And to bring it all the way back around and close up here, so what I actually do, like in my day job as a solid-state physicist, I grow crystals with different concentrations of cobalt and iron. So I mix out the ratio of cobalt and iron. It's almost like I'm cooking and I'm trying different amounts of like sugar and salt and stuff like that. So I change those ratios of elements and I grow different crystals and I see what their properties are. I can freeze the crystal and see how its properties change as a function of temperature. I can hit it with a large magnetic field and see how much magnetism you need to break the anti-ferromagnetic crystal. And I can study its resistance as a function of temperature, function of field, as a function of how much cobalt. So I can do a lot of things. I have tons of knobs to turn. So it's a very large parameter space. I don't know if you caught that. It's a big parameter space. Lots and lots and lots of things I can try. And what you see here is the crystal is on a, right, I'm pointing at the screen like you can see what I'm pointing at, right? So this is one of my crystals. It's glued down between these two titanium plates, and it's on a straining device. This lets me pull the crystal. And I said before that the spacing of atoms in the crystal is different for the two directions. As I pull on them, I can change the orientations of the magnetic fields inside of the crystal and also study the properties that way. And here you can see my crystal is inside of a cryostat at Argonne National Labs, which is a synchrotron. It makes X-rays. So X-rays come down this tube, hit the crystal, and hit my detector plate, and then I can really, really accurately measure the spacing of the atoms. So a lot of my research is on resistance and atom spacing of these crystals. And yeah, I'll finish up. So just a final shout out. Stephen Hawking. Fun fact, I think Andrew talked about it a bit, but one of the very last things he was working on was what happens to information when information falls into a black hole. So one of the very last things he was working on was information theory. And this URL, this barcode, this will get you to a YouTube video where I explain how I grow crystals and how I do the experiments on them with video, because that's much better than, with pictures. So, all right, thank you.